started the process. Right, so it is important for me to start the recording today because I forgot to do it in the morning class. So this is my last chance to record it for both classes, so it is kind of important. So I'm gonna take this out, and I can leave this one on, if you guys are curious. All right, so we have a new homework assignment. Okay, limited summation is the new homework assignment, and I'll just kind of describe what it is, just to make sure that you guys know what you're supposed to do. So in this case, I want you to write a program, create a folder called sum, S-U-M, and your source file itself should be named main.cpp. That really should not be a big deal at this point because we should be able to do it either using the command line, using Linux, or code blocks. Okay, in code blocks, just make sure that the name of the project itself is sum all by itself, and that will automatically create a folder. And main.cpp is the default name of the source file, so you don't really have to do anything special except to name your project sum in this case. So your program is going to do all of these things. First, it will prompt a user to enter a maximum number of entries. So the number of data points to enter, that's what it's asking. What is the maximum number of data points that it is supposed to collect? So here we have a little crude way to do the simulation. So I can just type pretending that in the C program. I'm saying that, okay, let's prompt. So the prompt is max pound entries. So all you have to do is to, in your program, print this particular string, max pound entries, and probably a space right after that. Print it to the standard output and stop right there, and then ask the user to input a number. Okay, so the number obviously has to be a non-negative number. In the previous class, somebody asked, can it be a 0? Well, yeah, it can be a 0, but if it is a 0, that means you're not going to ask for any actual entries. So for this example, I'm going to say, okay, let's say the user types 5. Press the enter key, and then the next question is, what is a threshold? Okay, so what is the threshold of the sum? And I'll talk about how to use this number later. So what your program needs to do is to print threshold to standard output, and then wait for the user to enter another integer. So in this case, let's say the user enters in a threshold of say 20. And here's the rest of the program. So the rest of the program is going to use error checking logic. You basically let a user to enter a base 10 signed number, which means it can be positive or negative, until at least one of the following conditions is true. Okay, they can both be true at the same time, but I'm looking for at least one of them to be true, and you have to keep doing this until one of these is true. So the first one is the maximum number of entries is reached. So in our example here, because I specified 5 entries, so that means one way to meet that requirement is I have entered 5 numbers. The second reason is when the sum of all the entered numbers has reached or greater than or equal to the threshold. So if one of these conditions is met, then you don't ask the user to input any further numbers. And then at that point, you will print the sum of all the entries, all the numbers. And in this case, you don't have to prompt anything, just print out the value itself is fine. So I'm going to run through a simulation here. So assuming that I'm the end user, I specify up to 5 entries and a threshold of 20. So I can now say, okay, 1, 2, 3, 4, 5. Now there are 5 entries here. The sum of these 5 numbers is
Less
what?
than 20, it's 15.
25. 1, 2, 3, so that's 6, 15, okay? So the sum is 15, which is not 20. So even though it does not reach the threshold, I have used up all 5 entries already. So at this time, the program will calculate the sum of these 5 numbers, which is 15, and it will just print 15 as the output, and that's the end of one case of executing this program. I'll give you another example. Maximum entries would be, let's say 4 this time, okay? And then we'll set the threshold to, let's say 100. So if I just type in one number, which is already exceeding the threshold, that's it, right? Because 101 is greater than or equal to the threshold, and I only need one of the 2 reasons to get out of to move on, okay? I was about to give away another 25% of your homework, solution. So I caught myself this time. Okay, so if the sum is 101, that will meet one of the two requirements. So it's time to move on. So moving on, it is just printing the sum or the total of all the numbers. Since there's only one number in this case, that is also the entire total, which is 101. So this is the second case of running the program, but using a slightly different input. Yep. You can put a negative number, but negative numbers are kind of tricky. Okay, I can give you one example. So let's say, well, this one you cannot use negative. Okay, the number of entries. If you specify a negative number, it's not going to work, right? Okay, the threshold also does not work as a negative number. Let me tell you why. If I specify negative 23 as my threshold, 0, which is the sum originally, the sum has to be start with 0, right? Because when you don't have any numbers, what is the summation? It's 0. 0 is already greater than or equal to negative 23, so you basically will move on right away and print a 0 as the total. I mean, I suppose you can do it. The logic will work out this way, though. Is that okay? Okay. Now, for each number that you enter, you have to do error checking. So error checking means entries that are not numbers are detected and ignored. Okay, so you're not going to process it, at all. You are to use printf and scanf in this assignment. You cannot use cin or cout. So what that means is, if I specify the maximum number of entries to be 4, and it doesn't matter, this part is just for the error checking. So let's say the threshold is just 5, and I type ASDF and then press the enter key. Your program needs to detect and say, oh, ASDF is not even a number. Nothing is processed. It doesn't count as a number, doesn't count as an entry, and obviously will not change the summation either. Is that okay? So until you actually type in an integer, it won't count as an entry. It won't affect the sum.
Okay, but so this is all fresh code we're running. We don't get no.
That is correct. There's no starting point for you to download. You just create your folder. If you're using Linux, if you're using CodeBlocks, you just create the project, which automatically creates the folder.
Have we, I know how error checking is, but have we talked about how to do that? What type of syntax you use to catch entry errors?
I think so. Let's go back and see. Okay, let us double check. Because last time I think we talked about how to get input from using scanf. And in here, we have something that looks like this. That's basically your basic mechanism of error checking.
Oh, okay.
Because scanf returns a number, and that number is the number of items that is parsed correctly,
okay,
the way you ask for.
Okay.
So if you ask for only one thing, and it comes back with a value of 0, that means you didn't get what you're asking for.
Okay.
So use that as your quote-unquote error checking mechanism.
Okay. I thought maybe you wanted us to write validations or something like
Oh,
that.
no. Just use whatever that we have already covered.
Okay.
Yep. So are there any questions at this point? I mean, the name of the variables is entirely up to you. How you want to structure your code is entirely up to you. But what I'll be checking will be from the outside view, whether your program works or not. Yes?
Can we learn something? Can we use something that we haven't learned yet?
As long as I know that, probably yes. Yep.
And you said with them entering a non-integer value, do we prompt for input or we kick out? You said when they in
That's up to you. Yeah, in the homework assignment, it is optional. So error checking means you don't have to complain about it. If you want to print an error message, you can do so, but you don't have to.
Oh, but no, but what I'm saying is the program should continue running. If
Yes.
they haven't entered, then
Yes, the program will continue to run, except it will ignore that particular entry. Right. So when you're all done, zip up the folder into a file called sum.zip and turn in the zip file. So that part is pretty much the same as all the previous assignments. Are there any questions about this homework assignment? No questions? Right. If there are no questions, we'll move on and continue to talk about we'll start to talk about C in and C out. That's what we'll talk about today. And it will also take a digression to talk about pointers again. So we'll go ahead and start with using C in instead of scanf, which is a pretty short document. Like printf versus C out, scanf also has a counterpart in C++. How many people still remember printf and how that compares to how did it compare to C out? A little bit? Right.
C out is more like a buffer, really, than just whatever you're sending to it, it's going to print.
Okay. Well, that's a fairly good description of what it is. Okay. First of all, printf is a subroutine. Okay. So you're calling a subroutine, and it requires at least one parameter. Okay. If you want to print a number, you basically have to use a placeholder, which is %d in this case for signed decimal numbers. And once you specify a placeholder in double quotes as a string, you also have to say, oh, this is just a placeholder. Let me tell you what printf is supposed to use to fill that particular placeholder. So in this case, because it is expecting an integer, so we'll have to supply an integer to print. Now, what you're supplying to print here, which I only use I, it can be any expression that becomes an integer. Okay, so 23 is just as good because 23 is an integer. 23 times I, assuming I is an integer, is also an integer. So what that means is this particular argument to printf, which is the value that you use to fill the placeholder %d, can be anything that is an integer. Okay, is that part okay? And that's how you print a value, an integer value, using printf. On the other hand, cout is not the name of a subroutine. Cout is actually the name of a variable in C++. Okay. Yep. It is representing what we call an IO stream. Okay. IO stream is the class, kind of like the type of cout, but cout itself is actually the name of a variable that is already defined. So this, which is also called the right shift operator or greater than, is actually an operator. Okay. Whoops, I take it back. Sorry. It should be the other way. It should be a left shift or less than, which is also an operator. And then you just have to specify what you're trying to print here. So using the same example, the 23 times I is an integer expression. And that will also print the value of 23 times I, whatever the value of I is, it will just print the product in this case. Okay, so those are the two ways to print something, as the output. The first one is printf, the second one is cout. And last time, did I contrast the two approaches, the pluses and minuses of either approach? Okay. The nice thing about printf is every single time you specify that you want to print something, you have to supply the entire specification. Okay, are we printing it in base 10 or base 16? How many digits am I supposed to use? Are we supposed to use leading zeros or not? So you have to specify the entire thing. Nothing is sticky. Okay, so after this printf statement, the next printf statement, you have to re-specify everything again, but then it can be completely different from the first one. Because between two printf statements, nothing is sticky, okay? Nothing is persistent across the two printfs. On the other hand, when you're dealing with cout, that's not the case. With cout, you can change the base. You can say, oh, now I want to print in hexadecimal. But once you change the quote-unquote mode of cout, it is sticky. From here on, every number, every integer is going to be printed in hexadecimal. Okay? Yep.
This is just an observation, but now that you said it's a variable, that actually, because the first time you said that, I I was like, that's a pretty stupid way to, because like if you change it to hex, it's going to print out no. But since it's a variable, that kind of makes sense because it's like you've changed the type of that variable.
Correct. Because as a variable, when you say cout less than hex, that basically changes a part of the variable, and it remembers that you want to print integers in hexadecimal. So the next time, without knowing the base, without specifying the base, it will go back and say, oh, I remember last time you wanted to print in hexadecimal, so I will use hexadecimal this time as well, which may or may not be what you want to do.
But it's just a result of them changing it to a variable instead of...
Correct. Because cout is a variable, it can remember stuff, right? As opposed to printf, which is just a function, it does not remember anything.
Okay. I don't know if this is, but do you know what's the programmable reason why they changed it to a variable instead of a subroutine?
Well, I'll address that later, okay? Because that's a very good question, but it relates to something that I want to go over anyway, which is a topic that we'll get to a little bit later, okay? Just a little bit. All right, so that's printf versus cout, and just like this is a pair, okay? You can use one or the other. The use of scanf also has a counterpart. The counterpart is cin, and with cin, this is the syntax that you use in order to read a integer into a variable x. In this case, I'm assuming x is an integer already, okay? Then this particular line, this statement, is going to read from the standard input file, interpret those characters as a base 10 signed integer, and then store that value into x. And, well, I don't know about you, if this is the first time I take a C++ programming class, I would have a question, because in scanf, I remember distinctly that we talked about the ampersand operator. Because we want to store into variable x, so we have to use ampersand to say, oh, let me tell you where variable x is so that we can put a value into it. That's why we have an ampersand. But how come in this case there's no ampersand? You can see that it's just x. It's not a typo. You really do not have an ampersand. And that's because in C++, this only works in C++, by the way. Scanf works in C and C++. This only works in C++. And that is because in C++, they have a concept called pass by reference, as opposed to pass by value. Okay? In C, the only type of parameter is passing by value. There is no such thing as pass by reference in regular C. In C++, there is such a thing called pass by reference. Okay, so some of you, I recognize that you came from my cisp360 class, so I'm hoping that you still vaguely remember what is passing by reference. Okay, and some of you do not come from my cisp360 class, you may not have encountered the term passing by reference. So I'm going to explain that. Okay, so I will explain and contrast what is passed by reference and what is passed by value. Okay. It works best, with like a prop here. So I'm going to say a subroutine is kind of like a cubicle, okay, with a person inside to do the work. Is that okay? So you have, as a cubicle, you have a wall, surrounding the subroutine from the outside. So for the most part, a subroutine has access to its own local variables and stuff like that, but it has very limited access to stuff that is outside of it. Is that okay? So when you want a subroutine to process a particular number, you have to pass that number as a parameter. So from that perspective, a parameter is more or less like an inbox, because that's how you can tell a subroutine and say, oh, I want to find the factorial of this number here. I want to find a factor of this particular number. I want to calculate the maximum of these three variables, and so on. Is that making any sense? Okay, a parameter is like an inbox, but it's not really an inbox either. So what I'll do is I'm gonna. An inbox is a tray. Okay, so let me get a regular inbox first and try to explain that. I don't have any thing here. Okay, so you can just kind of imagine that on this table here, there's an int tray. Okay, it's marked x for parameter x. Okay, so when we think about an inbox, it's pretty simple. Okay, I put a piece of paper here, and as a parameter, and then whoever is inside the subroutine will take that piece of paper and process that piece of paper. But that's not what happens when we have pass by value. Pass by value does not have an int tray. So what is a parameter? I call that an int copier. Okay, so think about it this way. I guess I can draw it on the whiteboard. So we have a cubicle here. Okay, so it's an enclosure. There's a person inside to do all the work, and this is the window, so someone can give the person something to work on. Okay, so traditionally in the physical world, we use a int tray where someone can put an item here, and then the person inside can take that item to process it. That's not passing by value. Passing by value is replacing this tray here with a copier. Okay, so if you want this person inside the cubicle to process something, you put the original item on the copier, and then you press the button to make a photocopy of the original item. The Xerox copy, the copy of the original is what this person is going to work with. And that's why it's called passing by value, because you only have access to the value of the original item. You don't have the original item. You have the copy of the original item. Is that concept working out okay? Okay, so let's put this to work first, okay, and see the limitation of this kind of approach. Okay. The example I'm going to use is swap or exchange. Okay, so we'll go ahead and write a simple program to illustrate the concept of passing by value, and we'll start to see the limitation of that concept. So we'll go ahead and I'll just call it swap1.cpp. So here is a subroutine called swap, and it has two parameters. The job of this subroutine is to exchange the values of the two things that I pass as parameters. Is that okay? Okay, because I don't want to specify the swap operation all over the place. Whenever I want to swap the value of two integer variables, I want to be able to call a subroutine and get it done. So let's just say that I'm swapping, integer values. So I have int x, int y as my parameters. And inside swap, I can use either the traditional code or the advanced, the more kind of tricky code. So I'm going to use the traditional code, which requires the use of a temporary variable as a local variable, which will store the value of x first. X then will be changed to y, and then y gets the original value of x, which was stored in t. And that's a very typical sequence of assignments to exchange the values of two variables. Are we doing okay so far with the code to exchange values? Okay, very good. So now we write the rest of the program. Here's main. Inside main, I have I, variable I initialized to 32, variable j initialized to 17. Okay, and this is one way to both declare a variable and initialize it at the same time. Okay, it's kind of like a shorthand thing. Whether you want to use it this way or just declare and then initialize later, it's kind of like a personal thing. Some people like it this way, some people like it the other way. It's kind of like a, it's hard to say which way is better. Okay, so that part is not as important. So now I want to say, oh, you know what? I want I and j to exchange their values. So now I call swap. I supply I and j as parameters, and that's my entire program. Okay. So what I want to know is, by the time I get to return 0, will the values of I and j get exchanged? That is the question. Okay. All right. So given this is the program, let's draw a picture representing this program here. And the side view is not going to work as well because we need two trays or two copiers this time. So we're going to use a top view in this case. So with the top view, we have now two copiers. One copier is labeled X, and one copier is labeled Y. Okay, to match the description of the function. When I try to swap the values of I and J, what I'm doing from the caller's perspective, from main's perspective, is to put the item I on the copier, put the item J on the copier, and press the button here and the button here to make photocopies of the value of I at that time and the value of J at that time. So what happens when you press the start button on the copier? You make a photocopy, right? So outcome a photocopy of I and a photocopy of J. A photocopy of I has a value of what?
32.
It has a value already. I was initialized to 32. So the photocopy of I would be 32, exactly. Okay. So this is 32, this is 17. Okay. And this piece of paper comes from copier X. This piece of paper comes from copier Y. So internal to the subroutine, this piece of paper is known as X. This piece of paper is known as Y. Okay. And inside, we have another piece of paper called T that is completely internal to the subroutine because it's a local variable. So the assignment operation is kind of like erasing one sheet of paper and copy the content of the other one onto the other one. So what we're doing is we are now saying, oh, look at the value of X. It's 32, copy it over to my temporary variable. And then I change X to become Y. So look at the value of Y, it's 17, update X to 17. And then we use T to update Y. So Y is no longer 17, it is 32. And that finishes the 3 assignment statements inside the swap operation. Now we are at the end of the swap subroutine. What happens to local variables or parameters at the end of the execution of a subroutine? They get destroyed, exactly. So now we say, oh, you know what? This piece of paper, and this piece of paper, let's throw all of them into the recycle bin. So what happened to I and J?
Nothing.
Absolutely nothing. Okay? So this is the limitation of passing by value. There's no way for a subroutine to change anything other than its own local variable, its own parameter, or global variables. In this case, variable I and J of main are not one of those cases. They do not belong to the subroutine swap. They're not global. So that means using only passing by value, there's no way to get to variable I and J of main from inside swap. There's just no way to get to it. Is that okay so far? And don't tell me just make I and J global variables. Okay, in this class we say global variables are evil. Okay, do not use global variables unless it is absolutely necessary. And there are very few cases where it is actually necessary. Okay, all right, so that's the limitation. Let's go ahead and compile and run this program anyway, because I want to see from GDB's perspective what it looks like. Okay, so we'll go ahead and G++ -G-O swap1 CVP list the program. We'll put a breakpoint on line 13 just about when we are just about to call swap. Run the program, print I is 32 just as expected, print J is 17 just as expected. Then we single step. Now when we single step, we are now inside the swap subroutine. Now GDB is very nice because when you step into a subroutine, it also shows you the values of the parameters, which is really handy. And it just says right here, parameter X has a value of 32, parameter Y has a value of 17. if you just look at this line here, is there any way you can link x and y back to I and j other than they just so happen to have the same value? Nope. That's exactly because they are completely independent from I and j of main at this point. It is just a copy. Okay? So I can do whatever I want with x and y and nothing happens to I and j. Is that okay? So we single step through this code, and by this time x and y should have exchanged already. Let's double check. X is now 17, y is now 32. Yes, we have successfully exchanged the values of the parameters to swap. What about I and j? Well, nothing should have happened to those. Now, can we see those things? Well, in GDB, actually, there is a way to see that, but I have to remember how to do it. Since I cannot remember, I'm going to say, oh. Now, that part has to do with either examining the stack or data. So, I would use help stack. Backtrace, frame, select and print a frame, stack frame. Okay, that's what we need to do. So we say frame. Okay, we can down select and print stack frame, call by this one. Backtrace of all stack frames, return select frame without printing anything.
Each function has its own frame, or
Yes, each invocation of a function has its own frame. So look at frame as a runtime instance of a subroutine. So if you have something that is recursive that can call itself, let's say 5 times, then you have 5 frames corresponding to one single function.
does main serve as like frame 0?
It's it counts backwards, so the most recent frame is frame 0. So that's why, in this case, main is actually frame 1 because it is one off from the current frame. What I'm trying to do is to see if I can, I can print x. Oh, okay, now it's back to main at this point. So I can print I and j. So print I, print j. Have they changed? Nope. So this subroutine is not working, okay? Because why would I make a swap subroutine when it doesn't do a single thing to the original item? It's just wasting cycles, right? Okay, that doesn't work. But it's close. The easiest way to make this program work, okay, let me make a copy of this. So copy swap1.cpp to swap2.cpp. And the easiest way to fix this program is to make x and y pass by reference. Now, do not confuse this ampersand with the address of, okay? They are related, but they're not exactly the same thing. When you're declaring parameters in C++, it only works in C++, but not in C. When you declare a parameter and you add a ampersand in front of the name of the parameter, it means this parameter is now passed by reference. Okay, so what exactly is passing by reference? I mean, how is it different? Okay, so let's go back and talk about this example again. Okay, so we'll reverse all of our steps here. And this part is still here. We still have parameter x, we still have parameter y, we still have the local variable t right here. And we are still passing, if you look at the main subroutine, I did not make a single change to the main subroutine. I'm still passing I of main to x. I'm still passing j of main to y. So now the question is, but what exactly am I passing? I still have 2 copiers. One copier is named x, one copier is still y. But what am I really passing this time? I'm passing a way to find the original item. Okay, so x and y belong to the main subroutine. So let's just call this. This is main. This is variable I. This is variable j. what I'm really passing this time is not a copy of I. It's not the value of I. It is a
Address.
I don't want to get to address because this is passing by reference, so it's not really quote unquote the address. So this is a way to find variable I. Okay, maybe it's just a GPS navigation thing, step by step, where to make a left turn and right turn. So it basically is a way and say, oh, this is a little map to find variable I. And here's another map here, which is how to find variable J. So each one is not the original item. It is the instruction to find the original item. Is that okay? But the copiers are still here. That means I'm taking this map here and make a photocopy of it. I'm taking this map here and make a photocopy of it. But then inside the subroutine swap, every time I refer to X, I'm looking at a map. Am I supposed to erase the map and move an integer into the map? How am I supposed to use the map?
Locate the original value.
Locate the original item. Okay, that is what's happening. So once I have the mechanism of passing by reference, I can now say, oh, t equals to x. What do we do with t equals x? Okay, t is right here. I need to overwrite this value with x. But what is x? X is a photocopy of a map, so I can find the original I. So that means I look at the original I, which at this time should be 32, right? Because it's 32 and 17 at this time. So I say, oh, okay, here's the original I. Let me copy that value over here. That's the first statement. The second statement is x equals y. So what is going to happen here? I look at y, because we have to evaluate the right-hand side first, and then we use the right-hand side to change the left-hand side. So the right-hand side refers to just y. I look at y, it is a photocopy of a map. I look at this map and go, oh, I guess I have to follow this instruction to go find y, and to go find whatever is at that location. I found this thing here, it is 17. So I copy that value of 17 to whatever is supposed to be in x, but I'm not going to overwrite the map itself. I will follow the map to wherever it leads me and change whatever it is referring to. So now I change this guy to 17. This is the result of executing the second statement inside swap. The third statement is to say, oh, take the value of t, which is my local variable, and then use it to update y. Okay, I'm not going to overwrite the map, a copy of the map to 32. I'm going to use the map to find the item that I'm supposed to overwrite. So now I go to this item here because the map shows me to over here, and I overwrite it with 32. And I'm all done. And guess what? I still have that habit of getting rid of everything that I don't need anymore at the end of a subroutine. So what am I getting rid of this time? A photocopy of a map, another photocopy of another map, and my local variable t. Is it okay to get rid of these items at this point?
Yeah.
Yeah, because the side effect is already done. I've already exchanged the values of the original items, I and j. This is passing by value. Okay. Let's go ahead and check it and see whether it works or not. And also, if it does work, what does it look like in GDB? Because we know what it looked like last time when we only used pass by value. This time we're using passing by reference. What does it look like in GDB, and how can we tell that this is passed by reference, and the fact that it works too? Okay, so g++ -g-o swap2 swap2.cpp, maybe GDB swap2. Put a breakpoint on line 13 just like last time. Run the program. Now we are about to call the swap subroutine. Print I, 32, print J, 17. Just as expected, nothing tricky here. Single step into the subroutine. Things are looking a little bit different now. Remember last time it just says x equals to 32 and y equals to 17. This time it still has 32, but there's a little bit of mumbo jumbo here. Okay, the mumbo jumbo is basically saying x at this location has a value of 32. Y, which is at this location, has a value of 17. That is your map. Okay, the highlighted portion here is your map, and so is this one. Okay, this is a map that tells you, which thing or what is supposed to be referred to by X. It's a way to find the original item. So now that we know this part, let's single step through the first two instructions. I haven't executed the third one yet. So at this point, if I say print X, it says, oh, not just 17, it says X at this location has a value of 17. Okay, that is supposed to be I, right? How do I know this is actually I? Let's go ahead and change the frame again. Okay, so we'll change the frame, which is the context. Okay, look at the frame as a context. So right now we are looking at things from the context of the swap subroutine. Let's change the context back to main and see what is happening in main. Did I change local variable I of main at this point? That really is the question. So we'll use the same command to do it. I cannot remember the name of that. So frame, okay. So we say frame 1, and that will allow us to switch back to the main subroutine frame. And I can now say, oh, tell me what is I. Ooh, I has changed already. Okay, and then the second thing I can also do is to say, I have a suspicion that I and parameter X are related somehow. Okay, let's check the address of I. I think we have seen this number before. As obscure as it is, we have seen it before. If I scroll back a little bit, when I print X, parameter X in swap, it says that X is at this location. That is the same address as I. In other words, a pass by reference parameter is implicitly an address of somebody else. Are we doing okay so far with that concept? Okay, and that's why this code works, okay, because of, I just kind of explained it in an animation of how it works. Is that okay? And cin uses this mechanism. That's why you only have to specify X and not ampersand X, because the second number, the number or the variable to the right hand side of the right shift operator, is passed by reference. Okay, now let's look at another way to do this. Okay, so what if we are not using C++? What if we're using basic, just plain old C? How do we do something like this? So we'll copy swap 2 to swap 3, and we'll answer the question of what if we are dealing with just regular C and not C++? Regular C has no pass by reference whatsoever, but it does have the concept of a pointer. Okay? Remember last time we talked about scanf and how we can use the address of X to give to scanf, so that scanf can actually alter the content of variable X. We can do something like this here. Okay, so what we do is we say, okay, this is a regular C program. We cannot pass by reference. But I can certainly say the address of I is here and the address of J is here. So I'm passing by the address this time. But that's not going to work. Okay, this is not going to work because C and C++ are both what we call strongly typed programming languages, which means an integer is not the same thing as the address of an integer. They do not match. Okay, because in this case, when you look at the prototype of swap, which is referring to this part here, swap is clearly saying X has to be an integer, not the address of an integer. Y has to be an integer, not the address of an integer. But what am I using to pass as arguments to those two parameters? I'm saying, let's use the address of I. The address of I is the address of an integer. It is not an integer itself. And the same thing here. This is the address of an integer, which is not an integer. Is that okay? So if I try to compile this program, g++-g-o swap3.cpp, it's going to complain, and that's exactly what it's complaining about, is there's no way to convert an integer pointer to an integer. Okay, it doesn't know how to do it. Okay, so to fix this problem, we can now say, oh, it's my mistake. I did not tell you ahead of time that we are now expecting a address of an integer. So what I'm doing here is the asterisk. Remember how we read this in the backward way? This basically is saying, let me highlight which part I'm talking about. This part is now saying x points to an integer, y points to an integer, which is the next thing. Okay, but it's still not passed by reference. This is actually passed by value. I'm making a photocopy of the pointer itself. Are we still doing okay so far? Okay, now let's see if we can kind of do this with our analogy. But this is not going to compile. Can you tell me why this is not going to compile? Main does. I mean, yeah.
Oh, because it's before.
Trying to assign the.
Yep. Yep. If you let's refer to line numbers here. What is the first line that's going to have a problem here? Yep, line 4 is going to have a problem. What is the type of the right-hand side of line 4? What is x? A pointer, an address to an integer. Okay. What is the type of the left-hand side of line 4? Just a regular integer. Once again, the types do not match. Okay, and this is not one of the cases where coercion will work or type promotion is going to work. That will work when you have a shorter integer versus a longer integer. This is not about the width of the integer. Okay, one is a pointer to something, the other one is not a pointer. So there's no way to automatically convert the type, and the compiler is going to complain. Well, we'll go ahead and let the compiler deal with this and complain about it. So this is the complaint. Exactly what we were expecting. Invalid conversion because a int pointer or the address to an integer cannot be converted into an integer without some additional work. How do we convert a pointer back to what it points to? The asterisk operator, which is known as the dereference operation. Okay, I'm not sure whether we talked about this before, so I'm going to do it, and then you can tell me whether we talked about this or not. Have we talked about this operator? Nope. Okay, so we'll talk about it now. Okay, this is called the dereference operator. Okay, let me take a step back and say, let's say this is the first time I take a C class, and I say, oh, you know what? One way to fix this problem is to make t the same type as x and y. Okay? Like so. Okay, now t, x, and y are all of the same type, and all the assignment operations will work just fine, right? Okay, good. Let's see if we can compile this program. G++, it compiled just fine. And let's see if we can run this program and see whether it works or not. Now, this is really the worst part of this entire class, is because the code is wrong. It is not supposed to work, but it does. Let me say that again. The code is wrong and dangerously so. It is not supposed to work. There's only a very slim chance that it would, and it does in this case. Okay. However, I can still demonstrate the danger. Okay, what is the big deal? Okay, so let's go ahead and look at the big deal here. So we'll list the program, and you'll figure out, okay, line 13 is still my breakpoint. Okay, so I will run the program all the way up to line 13. Print A, print I, print J. Okay, that part is pretty cool. Same stuff. Single step. Okay, now let's take a look here. Well. As Iraj always say, well. Have you guys taken the class from Iraj Subsaveri? No? Okay. No wonder no one catches that. Yeah. Okay. Do you recognize this address? Yeah. So passing by address or passing by pointer it's really doing about the same thing as passing by reference. Okay, and the other one obviously is referring to the address of J. This is the address of J, this is the address of I, so I'm just passing the address instead of the value this time. No big deal. What about T? Okay, X and Y are parameters. What is T? It's a local variable. Did I initialize T in the original
I
code?
see. Is it that every time you come back to the subroutine, T may have a different
Yes.
address?
T, exactly. T stores a different address. Okay? That's not good. That is not good. Because now I can say, oh, what exactly is T?
This code.
Is that a location that we recognize? Is it the location of I or J? It's neither of those two. So we don't really know whose address it is, and it just so happens to be a place where you can actually overwrite in this case. Now, because it is uninitialized, okay, it can very easily have the address of a location that you cannot overwrite. And when you run the code, when you try to dereference it, it's going to crash the program, okay? Okay, but that part is not even important here. Okay, let's figure out what this code is going to do, because this is not going to crash at all. Okay, this code is not going to crash because it doesn't do anything useful. Okay, so let's figure out what it's trying to do. What am I doing here? Let's just focus on one single line, one assignment statement here. X is a pointer. T is a pointer. In the assignment here, do you see an asterisk here, which means dereference and say, oh, I don't care about the pointer itself, I want to get to where it points to? Do we have an asterisk here? No. So we are referring to the pointers themselves. So basically what we're doing is, hey, look at pointer X. Copy the address stored in pointer X to pointer T. We are copying the pointer. We are making photocopies of the map itself. We are not following the map in any way. We're just saying, oh, here's a map, make a photocopy of it. That's what we are doing. So we single step, and one more time. Now I'm curious, what is X and what is Y? Okay, print X, print Y. What has happened here? I have exchanged the two maps. Okay? If you look at the original value of X, which is FBFFFFA24, it is now in Y. If you look at the original Y, it had the value of blah 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 A20, it is now in X. So what I have done so far is I was given two maps, and I have exchanged the maps themselves. Have I used the maps at all to find something? Absolutely not. Okay, wait, hold on a second here. Those are the maps of whom? Of I and J of main, right? But I didn't do a single thing about following the maps. I was just busy copying one map over to the other map and do the other thing around, right? I didn't really follow the maps to do anything. So what do you think happened to I and J?
Nothing.
Absolutely nothing. Okay? All right, let's go back to main and find out. Print I, print J. Okay, that's not working. Okay, so the problem was I was only dealing with the maps, not where the maps are leading me to. Without the dereference operator, the single asterisk symbol, the unary operator, I'm only playing with the pointers. I'm only playing with the maps. No wonder, nothing happened to the items that the maps were supposed to lead me to. Is that okay? Okay, well, that's easy to fix. We just need a whole bunch of asterisks to fix that problem, right? So now we copy swap 3 to swap 4. Swap 4.cpp. Okay, so my mistake is forgetting the dereferencing. So now I just add a dereference to everything. Okay, so now I'm saying, look at the map. Okay, X is a map, follow that map, go to the item at that location, and do something about what is at that location. That's what this is saying. Okay, do you think that's gonna work? It's not supposed to work, but it does. Okay, so we'll take a look at why this is gonna work. And in a very, very, very bad way. Yep, there is such a thing called, it is working, but in a very bad way. Because it's masking a problem. So swap4.cpp, gdb swap4. Once again, we put a breakpoint on line 13, run it up to there. I and j are still the same, no big deal here. Single step, x has the address of, hey, I thought I changed the code. Did I? Or did I forget to save?
Are you using the same? You copied it to a different file, right?
Swap 4. I forgot to save, I think. I mean, I can roll back my video and find out where I made that mistake. It's actually doable. Don't laugh. As I am recording, the file is accessible and playable. I'll show you. You guys don't believe it, right? VLC can do it. VLC, this is 2014, 1022, cisp360. Okay, so, and it's not going to screw up the recording either, so it's going to be okay. Okay, so this is the actual recording, and I can't really do any control because I can't see the this part here. Okay, now I have a thumbnail. I can go all the way back to where I was a little bit earlier before. Okay, I made all the changes, and then what happened? It's still playing, I'm probably still yakking. I didn't turn on the speaker. It's probably not necessary.
No, it's just sitting there.
No, I'm doing.
It's moving. There it goes.
Okay, so I did not. Oh, that's what I did. I typed Q exclamation point, which means I know what I'm doing. Let's quit. Don't worry me that I have not saved the file. I know what I'm doing. I just pulled a sledgehammer on myself. Yes, I know what I'm doing. That's what he likes to say. Yeah. Okay. Well, that was certainly helpful, right? It's like TiVo. I can just do it to myself. It's like bloop 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 bloop. Okay, so that's what happened. You know what? I know I'm just kind of half joking here. It may not be a bad idea to screen record when you write programs. I'm not kidding. No, if nothing happens, then you can just go ahead and toss away the recording, right? But in case something does happen and you cannot remember what I did, you can just roll back the tape. And in case there's a mystery you cannot solve, you can push it onto YouTube, mark it as not private but unlisted, send a link to me and say, okay, I want you to take a look at this time to this time here, and this is something I cannot figure out. Okay, I do this and I'm supposed to get this result, but I'm not getting that result. What is happening here? If I can do it with just free tools, without using any paid tools, so can you. You can do it with VLC itself in Windows. All right, so now I'm pretty sure I saved the file and then recompile g++ -g-o swap4.cpp. Okay, gdb swap4. Put a breakpoint on line 13 again, run the program, single step. Everything is exactly the same as last time, but I'm about to execute line 4, okay? So this time I have an asterisk operator, which is the dereference operator, in front of everything. All the pointers are now being dereferenced. In other words, I'm not erasing the maps and overwriting one map with another map. I am following the maps to go to whatever the map is leading me to and use whatever is at that location the map is showing me, and that is the stuff that I'm using, okay, on both the right hand side and the left hand side. So I would use X as a map, go to wherever X is leading me to, which I know exactly where it is I of main, right? Because that's how I pass the parameters. And use it as the right hand side. The right hand side of an assignment is just the value to be used to update the other side. Okay, so now I know I'm using the value of I as a local variable of main as the right hand side. Okay, that's cool. The left hand side is telling me what I'm changing, right? So what am I changing here? I'm not changing T, which is a map. I'm changing wherever the map T is leading me to. Is that okay? Because whenever you see the asterisk symbol, it's saying follow this map, go to wherever this map leads you to. And what is on that map?
We don't know, because we didn't.
Nobody drew anything on that map. It's just a piece of paper that somebody left behind from last time. Great.
So that's why this program is probably not a good way to.
That's why this program is very likely to crash. Because if you just randomly grab a piece of paper, interpret that piece of paper as a map, and try to get to the location, it's probably not somewhere that you can actually go to, right? Except in this case, it's a fluke, okay? It just so happens that T is a valid address. If you look at the range of the addresses, this is X, this is Y, and this is T. They are close enough, okay? They're not exactly the same. They're off by, let's see here, C4 and 24. They're off by, this is 1210. They're off by 160 bytes, okay? Which is not really a whole lot, okay? It is still saying, yeah, it's kind of a location where you have access to. Exactly whose location is it? What is it useful for? Somebody left behind a map and it leads to somewhere. I'm supposed to go there and modify the content at that location. That's what this line is going to do. Okay, so that's why I said when you're lucky, it won't work. It will be an invalid location and you get a segmentation fault right away. This is not good because it works. It's not supposed to, but it does. So if I single step, not a problem, okay? I just corrupted the content of somebody else. But I don't care because I got my job done. I return to the main subroutine and I say, hey, guess what? Main is all done. Okay? So in this case, the symptom of this problem is not showing up. Okay? It's just a fluke that we are just lucky that that location was not really used by anything. Okay? Well, not anything that would cause the program to crash or misbehave. Okay? But in general, something like this, you are lucky if it crashes right away when we had star t equals to star x. That would be good if it crashed right away. If it doesn't crash right away, that means you're changing the content of some memory location that is probably important to somebody else, and the symptom will only show up much later. How much later? Depends on your program, depends on how it's structured, depends on what you're modifying. And that is the worst kind of thing that can happen, is it doesn't happen right away. The problem is not showing up when it does happen. It is now showing up much later, and you will be starting to suspect the problem comes from somewhere else. How would you know that it happened here at this point? There's no way to go back. Yep.
The C++, because you said 160 bytes, does C or C++ have like a limit of how far? Like, so if this came up and you were 200 bytes past that, would it say, okay, that this is a match, you're probably not wanting to do this? Even though that's not like something you would rely on, but is there just one thing language itself? Okay, like, so 160 bytes was fine for us to like write over beyond where our code is supposed to be at.
Well, we are actually dealing with a stack here, and the stack is pretty big. I mean, you have a pretty big range of memory as far as the stack is concerned. And the fact that that particular position turned out to have a value like this is probably because before we even run main, there's some initialization code that all C program has to go through. And part of that initialization code left this behind. Because when you unroll the stack, you're not really destroying the content, you're just changing the marker, the stack pointer. And whatever it was used, it leaves behind its old value, but even though it's of no use anymore to the system, it leaves behind the value. And that's why it is quote unquote initialized. It is just so happens that in this case, it maps to a location that you have access to. But in general, it is not the case.
Oh, no, so yeah, that's what I'm asking, is that when a function or invocation function rolls out some bit of the stack, is there a size to that stack?
Yes. Yeah, we'll that is a topic for cisp310. And many of you will be taking cisp310. Now that you have seen this, by the time you get to cisp310, about this time of the semester, we'll be dealing with this sort of thing. Okay, because we'll be looking at the code behind C code in assembly language and how the memory is actually utilized. Then we'll be able to look at all these things again and say, oh, so that's what happened in cisp360, when we had a problem like that. All right. Well, we are running out of time today, so I'm going to end the lecture at this point. And it's going to be the same for both the early and the late class. I cover exactly the same material this time, so that's why the video is going to be shared between the two sections.